But modern physics is the era that started around 1895 and on.
That's a Ian.
Okay? Now, that seems like a really long time ago, but actually it's quite recent, actually. And the beginning of all this was when they started to discover what's going on with atoms, okay? That's where all this began, okay? So, the Greeks, as far as we know, were the first ones to come up with the idea of atoms, okay? I believe, if I remember correctly, it was some philosopher that was smelling baked bread and got to thinking about, well, how the heck am I actually smelling this bread?
Oh, yeah, I remember that story.
There must be little tiny particles of the bread floating into my nose for me to experience the smell of the bread. Actually, it's a pretty genius idea. And he said these little indivisible things were called atoms, little bitty smallest parts of an object, all right? All right, and that was way, way back. Okay? Now, in the 1880s, there were a lot of things that leading up to atoms and what they were like. Avogadro in the late 1700s and early 1800s, periodic table, 1869, Faraday in the 1800s with electrolysis. There's a lot of different things that they were discovering about atoms. But in the 1880s, you could establish the approximate size of an atom. Okay, so let's do that quick. You ready? Get out your calculators.
You're not going to worry about something until it actually happens. Okay. I'm talking to myself over here.
You're like, just like who's even talking?
All right. There's the density of copper. And there's the atomic mass of copper. Okay? And you also know Avogadro's number by this time.
Yeah.
So number Avogadro is 6.02 e to the 23rd atoms per mole. Okay, with those three ideas, actual density of copper, the atomic mass of copper, and Avogadro's number. All right, will you please figure out what is the volume of a copper atom?
Come on, buddy, we're almost there.
Just give it a little pep noise.
All right, density equals mass or volume. So I'm going to take a mass of 1 mole of copper divided by a mole, the volume for 1 mole then. But the volume for 1 mole would be Avogadro's number times a single one, right? Okay, so I just rearrange it like this and then plug in my numbers, right? And you should get 1.8. Yeah, roughly 1.2 e to the negative 23rd. That's centimeters cubed. If we convert that to meters,
Oh, it's too small.
it's 1.2 e to the negative. Okay, remember you convert to meters, you got to divide by 3 or 100 3 times, right? So it moves at 6 places. So negative 29 meters cubed. All right?
I mean, what? That's small.
That's ridiculously small. Okay, so the deal is that in the late 1800s, they could figure out what the size of a single atom had to be like. Had to be like this. Okay, now,
They just couldn't see it.
yeah, they just can't see. That's too small to see, right? So they're like, okay, this is why we can't see them. because we can't see anything that small. Now, at the time, they didn't know a whole lot about light and some of that stuff yet, so they were thinking that maybe perhaps they could magnify it enough to eventually see it. We know today we cannot see this because this is smaller than the wavelength of light that we see with our eyes, so it's impossible for us to see that small. Okay, everybody. Now, what's the shape of the atom? Well, they don't know because they can't see it. So it could be like a cube,
Square
or it could be round. Okay?
Or it could be like a star.
It could be. Now, however, they knew about crystal structures. Okay? There are different types of crystal structures. There's structures like this. There's structures that are like this. Crystalline structures. Okay? And a lot of people believed that the atoms had to be little spheres. And the reason why they believed they would be little spheres is because you can make all of these crystal structures with really tiny little spheres. Like, for instance, this one, you'd put a sphere here, 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 and here, and you'd have a square, right? This one, you'd put a sphere here, 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 and then one in the center, right? Hexagon. Okay? So every crystal shape that they had discovered, you could create with a bunch of tiny little spheres lined up properly. Okay? So if this is a sphere, then the volume is 4/3 pi r cubed. So what's the radius of an atom?
That stuff.
What's that? Actually, of a copper atom.
3/4 over pi.
And divide by 4/3 pi, and then take the cube root. What do you get?
You get a small number.
You get e to the negative 10th, right? I think you get 1.4 e to the negative 10th, right? Somewhere in there?
Like the radius is greater than the volume.
Yeah, because remember when you multiply numbers that are small, even when they get smaller still. Like 0.5 squared is 0.25, or small. All right, so we get about this, right?
Wait, so, but if you think about that in like sphere, that means it's like flat. No.
No, it's not flat. That's the radius.
How do you have a radius bigger than your volume?
Because remember, volume, it's a different type of measure. That's a cubic measure. This is a linear measure. Okay? All right, so you get about 1.4. You can do this for all the atoms that you have this information for. Okay? And you get somewhere between about 1 to 3 times 10 to the negative 10th. Okay? And they gave that measure a name. In fact, they called e to the negative 10th, or times 10 to the negative 10th, they called it this. It looks like a capital A with a circle at the top. It's called the atomic measure, and the name for it is called an angstrom. It looks like the Angels, if you're a baseball fan. Now, when I was in high school, they were still using this unit called an angstrom. Okay?
Do we need to know it?
A-N-G-S-T-R-O-M, I believe, an angstrom.
Yeah.
Okay? Now, you won't see an angstrom anymore because now the standard unit of measures they use as like milli, and then they use micro, and then they go down from that. So what you'll see is 10 to the negative 3rd, which is milli, negative 6th, micro, negative 9th, which is nano, negative 12th, which is pico, pico, femto, atto, I think, but after that I don't really care. Okay? They made up a new measure for it, called the atomic measure, or angstroms, all right? Anyway.
Sound like Nancy.
So they knew the size of it, they just couldn't find them. All right? Now, along this time, in the late 1800s, was a very interesting time in physics, because at this time, they had discovered most of what they thought was out there. They discovered that light was a wave, finally, because of the double-slit interference experiment. They hammered out all of Newton's laws and gravitation. They explained why the planets moved the way they did. They discovered electricity and magnetism and figured out induction and all that stuff that we just got through studying. All the optics stuff we've studied, they went through already. And so everything that we've studied in Physics B, they'd already figured out, finally. They figured out exactly how energy works, too. That was a very tricky one for them for a long time. Okay? And they didn't know everything about an atom. However, they knew its size, okay? And they knew that they were there. They just hadn't gotten down to it, and they were pretty sure that when they got there, the physics that they already had would describe the behavior of atoms, right? So, no big deal. And so most physicists around that time were what we would call determinists, or they believed in determinism. There was a great feeling that the universe was like this great big machine, okay? The weather systems were these great big machines. The way the continents moved, it was all a great big machine. And if you understood the physics and you understood the initial conditions, you could work both forwards in time and backwards in time and figure out how things would be in the future and what they were like in the past. Now we really, you might not realize it, but we've done that already. So we launch in trajectory motion. It's like, well, where is it going to land? We predict in the future where something's going to land, right? And we've done that a lot in physics already, okay? All right.
What about moving back?
And that was also their thought, is that once they understood everything, that they would be able to go backwards in time and figure out exactly what things were like in the past. So in theory, according to determinism, you could figure out what all the temperature is on the planet, how much sunlight's going to be hitting the planet and all that, and you could predict what the weather's going to be like in 5 years. Okay?
That'd be pretty cool.
Yeah. Very
No,
cool.
weather predicting doesn't seem to work very good here in Texas. Not in Texas.
2 years.
We
Exactly.
can predict everywhere
Exactly.
except
All right?
Actually,
Now,
don't live there.
what's truly astonishing is that in this environment that they were pretty confident that they had everything pretty well in order, okay? That over the next 30 years, from 1895 to around 1925, that all of the laws of physics, except 4, were proven to be incorrect. Okay? That they were good approximations. In fact, excellent approximations. Like F equals ma is great in the world we live in, but it's not perfect. You can reach extremes at really high speeds or really high gravitational fields, things like that, where it falls apart and fails to work. Okay? Now, in the world we live in, it's perfect. Okay?
Wait, so does that mean that maybe we could go faster than the speed of light if there's all these exceptions?
Well, as far as we know, we think that scientists, physicists, think that you can't go faster than the speed of light. However, there is a slight loophole. From what I understand, I don't know it all, but from what I understand is that something with mass cannot get up to the speed of light. Only things that are massless can travel at the speed of light. So light, which has no mass, can travel at the speed of light. Okay?
Energy is mass. By the time you reach the speed of light, you have enough stuff that's converted all mass to energy.
Yeah, so if you can convert your mass into energy, then you could go the speed of light. However, there is a loophole. There is a loophole that some physicists believe in. I don't know if they still do or not, but that if the object was created and going faster than the speed of light, that it could be faster than the speed of light, but it would have to be created from energy into something that was already going faster than the speed of light. I don't know. There's all these exceptions that they still don't know. Okay? And physicists nowadays are a bit more humble than they were back then because they know that there's always stuff out there that you just don't know. Right? It's things that we don't know
They're not
about.
killing
Yeah.
themselves trying to find out everything.
Oh, they're trying to.
They're
But
killing themselves.
yeah. And what's really crazy is only Maxwell's equations of electricity and magnetism survived. Okay, relativity throughout most of the classical physics equations that we have, that they're not exactly right. They're great approximations when you go slow speed, but once you get up to about the 10th the speed of light, most of the physics we've talked about falls apart. F equals ma falls apart. Momentum is still good. Conservation of momentum, conservation of energy still work, but we're going to talk about those, how we have to modify them slightly. Okay? And in this time period, they discovered all sorts of things. They discovered the atom. They discovered X-rays and gamma rays. They discovered that the atom was not the smallest thing. They discovered electrons and protons and neutrons. They discovered radiation. They discovered relativity.
Just discovering all this stuff.
Yeah, this time period, this 30-year time period, there was more discoveries in physics than ever before, all concentrated in this one batch. They discovered antimatter. Now, antimatter may have come out slightly later than this. They discovered, we'll talk about antimatter. They discovered the photon of light. That light is not a wave, exactly. It's something different and new, a new description. They discovered quantum physics, and they discovered Heisenberg's uncertainty principle, okay? And what they discovered, amongst other things, is that determinism is not really the way it works, okay? When you look at things that are large, like us, you can determine what the object's going to be doing in the future and in the past if you know everything. But when you get down to the small level, what you find is there's this fuzzy unpredictability, this fuzzy reality, where you don't know exactly what's going to happen, okay? And so you can put limits on things, but you can't tell exactly what's going to happen. All right? Like, for instance, the weather. They found out, I think this was maybe a little after the weather, after this time period, but for weather prediction, they found out that there's no way to predict the weather. You can't actually accurately predict the weather, okay? Because it's a chaotic environment where one change here changes things everywhere. Okay, a couple of quick stories about this time. One of the interesting stories was about, actually they consider this the beginning of modern physics, this one discovery, okay? The first thing of many that they couldn't adequately explain, all right? And this was by Wilhelm Röntgen in 1895. He was playing around with a thing called a cathode ray tube. You know what a cathode ray tube is?
This thing.
Actually, this is very close to a cathode ray tube, okay?
The tube.
All right, it's an evacuated tube for which they put high voltage from one side to the other. When they put high voltage from one side to the other, they would get a ray that would go from the negative side to the positive side, okay? And they knew it went from the negative side to the positive side because they get a tube, they'd evacuate it, they'd put a negative and a positive plate in here. So here's the negative plate, they'd have a variable voltage source, they'd crank up the volts, and off the negative side a ray would go across. And they could see the ray because they'd leave a little gas in there and the gas would glow. Or they could put a screen in there called a scintillation screen where it was like a fluorescent material so that when the ray hit the fluorescent paper, it would make it fluoresce green. Okay? Now they knew it was going from the negative side to the positive side because they could put something up here and it would create a shadow this way. Okay? All right, well they're trying to figure out what's going on with this thing. All right? And we don't know for sure if anybody else noticed this before Röntgen, but we do know that Rontgen discovered this, and he was the first one to investigate it. So what happened was is they would take pictures of this because they would put magnetic fields here. And when they put a magnetic field across this, the thing would turn. And it would turn. It would turn downward.
Oh, wait.
Because the beam would turn this way. And the way they would measure the angle or the radius of the turn is they would take pictures of it. Okay? With an old style camera, with old style film.
Well, that poops out.
And
Polaroids?
no, Polaroids are way more advanced.
Yeah.
Oh my gosh.
So they'd take a picture of it, then they'd develop the film, and then from the film they'd measure the curve. Okay? And they knew that if they put an electric field in here, so it's going across this way. If they put an electric field in here like this, so if they put a capacitor plate across here, and the electric field went like this, it would also turn downward. So they knew that this beam must be negative. It made up of something negative, right? All right, they're taking pictures of it. Well, Rontgen had his photographic paper in a box, okay, that was covered up to keep it light tight, so it was dark inside. And they'd turn off the lights inside the room, and they'd take the paper out because it's sensitive to light. He'd put it in the camera, take a picture, close the box back up, go develop it, and then look at the picture. Well, he noticed that when he had this close to this cathode ray tube, that the film would be ruined. Okay? And he's like, huh. He had his hand over the film. And when he developed the film, he got the first X-ray picture, complete with bones, and you could see his ring on his finger. He's like, what the heck is this? So he discovered X-rays. And they're called X-rays because he had no idea what they were, and he called them the unknown X-ray. All right? And he knew he only got these from this thing. And he knew that they were coming off this side right here. Because when he did the film over here, he didn't get it. Okay? All right, and he's trying his best to figure out what the heck's going on. So he kind of locks himself away in his laboratory for a couple months, pretty much. And his wife is like, what is going on? So he takes his wife up there and he says, here, put your hand on this.
Yeah, and let me kill you.
And he takes an X-ray.
So death do us part.
He takes an X-ray of her hand. And when he develops it, she's like, ah, it's the work of the devil, and she never wanted to see it again. And so for about 3 months, he tried to figure out what it was. He publishes his results, I think in January. This was like October or November when he discovers it. He publishes his results, and he becomes famous, and the X-rays become famous, and immediately go to work in hospitals because they can see inside your body, right? And they try to figure out what this X-ray is. So they try to take the X-ray and they try to bend it with magnetic fields and electric fields, and it doesn't bend. So they have no idea what it is. Okay? So that's kind of the beginning of modern physics.
I still don't know what it is to this day.
No, to this day, they figured it out. What they figured out was that it was one of Maxwell's electromagnetic waves, like light. So it was added to the grouping of electromagnetic waves that Maxwell had predicted with his equations. So light is an electromagnetic wave, X-rays are an electromagnetic wave. It wasn't until later that they all put them in one single spectrum, that they were all the same thing really with just a different frequency. All right? All right, so did all that. They actually figured out that this cathode ray is actually electrons flying across there. Because what they were doing is they had a large enough voltage across there that electrons, the valence electrons, were popping off of the metal and flying from the negative side to the positive side. Okay? Millikan's oil drop experiment happens in there. They discover radiation, radioactivity, and what they find with radiation is that they had some materials like uranium or radium or some of these things, and they would put them next to photographic plates like this in a box, and they would also develop the film. So they said, oh, so we got rays coming off of this too. What kind are they? So they identified 3 different kinds. So they'd have a radioactive material, and then they would send it through the rays, through magnetic and electric fields. And they found that some of the rays did this, some of the rays did this, and some of the rays went straight through. They called this one alpha, beta, and gamma. Alpha, beta, and gamma rays. The alpha rays turned out to be a helium nucleus, a +2 helium nucleus. Okay? So if they go through a magnetic field and they turn upward, that follows the right-hand rule, correct? So that's positive. This one's following the left-hand rule. A beta particle turns out to be an electron. Okay? It turns faster because it has less mass. You remember all that stuff?
Yeah.
So that we have QVB, magnetic force, equals mv squared over r as it goes through a circle. And so you get the radius equals mv over qb. Right? So they use that a lot. And this one went straight through. They eventually called this a ray, left it as a gamma ray. Turns out to be an electromagnetic wave, just like an X-ray. So they discovered 2 new ones in the span of 10 years. Okay? All right.
They've been the happiest geeks alive.
Oh, man. It's crazy time.
Wow, 2 things.
Because physics essentially was falling apart and being rediscovered. Really pretty cool, actually. Actually, it's a lot like biology right now. Okay? Chemistry's big transformation they went through several transformations. One, when they discovered a lot of the stuff in the 1800s with the periodic table and all that. And now, after physics discovered quantum mechanics and what the shell structures were like, Schrodinger's equation, which we'll talk about a little later, they were able to figure out the actual structure of the atoms and why molecules are the shapes they are. So all that stuff's going through. Yes, molecular geometry and all that stuff. And then biology's going through grand transformation right now with the discovery of DNA and the genetic code. And so not just the genome, but the epigenome and RNA, which they thought wasn't a big deal, which is really a huge deal. So they're discovering more and more stuff every year in biology now. Now, here's the deal, everybody. They figured out that in radioactivity and from cathode ray tubes that the atom can split apart, that little negative things can fly off of it, and even big positive things can fly off of it. I say big, relatively speaking, right? So here's the deal. So what the heck is the atom like? They don't know. And so their idea was that the atom was this big positiveness filled with little negative things, which we call electrons, that could fly out, given a high enough voltage. Okay? Or potential difference. So here you go. So they developed what was called the Rutherford experiment, actually the Geiger-Marsden experiment. And here's what they did. They had a radioactive material inside of a big lead box. A big lead box that had a hole in it. Okay? And out of it pops alpha particles. And they know exactly how fast these alpha particles are going, because they send the alpha particles through this. And when they send the alpha particles through that magnetic field, which way do they turn? Okay, which way do they turn? Alpha particles. Okay, they're going that way. Right-hand rule, correct? They're going that way, B field in, so they will move up. So they're going to curve upward. But then they put capacitor plates right here.
Oh no.
And they want it to go straight. Positive on top, very good. Negative on the bottom. And it's going to go straight through. Now, here's the deal, everybody. You got to remember this. If the alpha particle goes straight through, both an electric and magnetic field, which are at right angles to each other, okay, then the forces on it must cancel, correct? That means the magnetic force must equal the electric force. The magnetic force is Q VB. The electric force is
KQ1, Q2 over all the way.
no. EQ. What happens to the Q? So the velocity equals E over B. Guess what? You tune your electric field and your magnetic field to predict or to pick the actual velocity you want. So sometimes this is called a velocity selector. So you select the velocity you want and you shoot it through. So they know exactly the velocity of the alpha particle. They also know the mass to charge ratio of it from this. They know the momentum of it. So they know how fast it's going. And here's the deal. They selected a speed that was going to be so fast that it should shoot through the atom. Okay? Because it starts off with kinetic energy, and when it reaches right here, it's being repelled by this big positive, right? Because the alpha particle is positive, right? It's repelled by this big positive. So it should come here and stop, and then turn around if it's shot straight at it, right? It should go, stop, and turn around if this positive is big enough, right? So it should end up being electric potential. So you get 1/2 mv squared equals VQ, right? Got it? Shh, listen. Right? And here's the deal. 1/2 VQ, and this is going to be equal to KQ1 Q2 over R squared, because we have a spherical charge here, right? Remember our atom? We assumed they're going to be spheres, right?
They're wonderful spheres.
Wonderful spheres. We know the charge of the atom we're shooting it at. We know the charge of the alpha particle. We know K. We know the mass and the velocity. So what we do is we shoot it at a velocity that's going to be so great that it won't be able to stop in time. That this radius is too big, because they know the radius of the atom. So what's going to happen is the atom can't stop it. It's going to shoot straight through. And so therefore, they're going to penetrate the atom, and they're going to figure out what the atom looks like inside by the way the alpha particles scatter when they go through. Does that make sense? All right. Well, here's what happens. They expected, when they shot this through, and V is KQ over R squared. I'm sorry, that's KQ over R. Sorry. So that's R down here, not R squared. Sorry. I did it again. They expected the alpha particles to come through here and then be deflected by these electrons. And that they would go through and deflect a little bit and then come out like this, and that they would get a blob on the screen. Okay? All right, so here's what they got. When they hit the screen, they get this. Nothing, hardly nothing, and then all of them right there, and then nothing.
It's like nothing happened.
Yeah, it's like it went straight through the atom, and nothing happened. They're like, what the heck? Now, so it appears like the atom's filled with nothing. And then the second craziest thing is that they just happened to check. They put the screen over here. They got a few. They put the screen back here, and they got a few that went all the way in and turned around and came straight back. We just said that that can't happen. That the positiveness is too big. Okay? So what they did is they worked backwards. They said, okay, if the alpha particle goes all the way in, stops and turns around, how small does this positive thing have to be? No. What they got was that the positive part of the atom was around 10 to the negative 14th meters across, even though we knew that the atom itself was 10 to the negative 10th meters. So the question is how does that work? And that's where they came up with the idea of, well, what happens is we have a positive nucleus, and this outside here is some kind of negative thingy. Negative electrons doing something. What? We have no idea.
Attractor, no.
Yeah. At first they said that they were going in circular orbits, but that doesn't work. Okay, so they don't really know what they were doing. But this is called the nuclear atom, or the Rutherford atom. Rutherford was the one that was in charge of this experiment. Geiger and Marsden were the ones that actually did the experiment. And Rutherford, I think, did the math to figure it out. Anyway, so that was when did that occur? 1909 was the experiment, but he didn't figure it out for a while on what exactly the atom was like. Okay, so from within 10 years, the whole model of the atom changes. Okay, that's pretty substantial. Okay, that everything changes. All right. Also in this time period, all right, you ready? Photoelectric effect.
What the?
Flux.
Okay, for those of you that want to make this a little bit more personal, photoelectric effect is a solar cell. Okay? All right. Scientists had stumbled onto this, and it goes like this. If you send light, which by now we know is a wave, because when we send light through this, we get this pattern. Right? Which cannot be done by anything other than waves, right? So light, bingo, is a wave. So 200 years of arguing about what light was, answered. Okay, so light comes down, hits this piece of metal. And just like in the cathode ray tube, where you had enough electrical potential difference, electrons in the valence shells would be ripped off and shoot from the negative to the positive plate. Well, here you could shoot light at this. The light would be absorbed, and an electron would pop off. Okay? All right. Light comes down, light absorbs. Now I want you to understand, the light disappears. Okay? And an electron pops off. Now, let's think about this in terms of energy, people. Energy of the light. Where does it go? What kind of energy does the electron have? Into kinetic energy. So this energy turns into this. Okay? Now, let's think about waves in the classical sense. Okay? If we think about waves in the classical sense, if I have a little wavelength or a little amplitude wave, then the electron should shoot off with only a little kinetic energy because this had only a little energy to start with. And if I shoot this with a really large wave, then the electron that pops off should have a tremendous kinetic energy, right? Because amplitude is equivalent to energy in a mechanical wave, right? In a classical wave. The bigger the wave, the more energy the wave has. Okay, well here's the problem. What they found out was that it didn't relate to amplitude or in light brightness at all. Okay? Like for instance, if I have this and if I shine blue light on it, a little bit of blue light, an electron pops off. If I shine big blue light at it, then electrons still pop off, but they both have the same maximum energy. Okay? So the kinetic energy of this one and the kinetic energy of this one are the same. The difference is that this one will produce lots more of them. Does that make sense? So we still have conservation of energy. I have lots more energy here, so more of them pop off. I have a little bit of energy here, so only one pops off. But the thing is the maximum kinetic energy in both cases is identical. Now that doesn't make sense for classical physics. Because the bigger the wavelength, it should not just pop them all off at the same maximum energy. It should pop off some with huge energy, right? It doesn't work that way, though. And here's the really crazy thing. If I was to shine red light on here, nothing. If I shine really big amplitude, bright red light, bright enough red light to roast you alive, nothing. However, if I shoot violet light at this, the tiniest violet light you can imagine, guess what? Electron. And not only electron, but electron with lots of energy. What the heck?
So frequency, wavelength.
Okay, so here's the thing. They find out that energy of an electromagnetic wave is frequency related. Okay? We'll continue this next time.